we saw 300 hosts per subnet, which is not matching with the real world. In real world, every department will have different size, different number of IP address needed, not the same. So we have to do different subnetting for each department. For example, if I have two routers and some switches, and some computers, we got 20 computers here, we just got 10 computers here, we got 30 computers here. Now, the number of IP address needed is not the same. If you see here, I need 20 computer IP address plus this port on the router will also be a member of same subnet. So I need 21 IP address here. And here 10 plus 1 plus 1, which is 12 IP address. Because it's a layer 2 switch. This end, and all this 10 computers, they will all be in same network. And here I got 30 plus 1, 31. So you need to do 3 different subnetting. If you do 3 different subnetting, will the subnet mask be same? For example, if 10 is the network that we are going to use in our organization, subnetting first we need to do for the small one. 10 IP address needed. Then you will say 10 dot for 10 you need these many bits. So the mask is going to be 10.0.0.0 slash 28. And the first subnet is 10.0.0.0. Second subnet is 10.0. What is the value here? The increment value 16. And goes on. It goes on like that. Now, what will be the first IP address in this department, in the subnet? 10.0.0.1. What will be the broadcast? 10.0.0.15. What will be the last IP? 14. If you notice here, you got 14 IP address in the subnet. How many you need? 10 plus 1 plus 1. How many? 12. 12 you need. You got 14 IP address. Good. See, if I would have done subnetting using this 30 as a number instead of 10, then there would be a lot of wastage. So we have done separate subnetting using 10. Likewise, you are going to do separate subnetting using 20 now, the next biggest. 10.0.0.0 slash 8 is the default. 10.1, 2, 3, 4, 5, 6, 7, 8. Now, for 20, how many bits you need? You need these many bits. Because if I take only this much, I'll get only 14. We saw here 1 to 14, 14 IP errors. But what we need is 20 IP errors, 20 plus 1, 21 IP errors. So we are going to take these 5 bits for host. And from here we are giving for networking. So what will be the mask? 10.0.0.0/27. You see the mask is not the same. Here it is 27, here it is 28. And now the next subnet will be 10.0.0. What is the phase value here? 32. 32/27. The next one is 10.0.0.64/27. It goes like that. Now you see, we should not use this one. Why? We have already given up to 15 for some other department. So don't use this. Use from here. So this is the subnet I'm going to give to this department where 20 IP address is needed. 10.0.0.32/27. Here what we have given 10.0.0.0/28. All right. So some IP address of this is already used in the other department. Only the mask is different, but the host portion is same. We have already used 1 to 14 here. So we should not use this first subnet. Do you understand what I'm showing you?
Yes, sir.
Okay. Now, you see the other one is 30 IP address. 10.1234567.8. Now for this also you need these many bits. If you take these many bits, what is the, see here, the first IP address is 10.0.0.31. The broadcast is 10.0.0.63. And the last is 10.0.0.62. Sorry, 31, this is 33. So 33, if you count from 33 to 64, sorry, 62, how many IP addresses you get? 31 IP addresses you get. 31 IP address. But what you actually need is 20. Here you need 30, so I can do the same subnetting as I did for 20. But we have already given this particular subnet for 20 host department. So we are going to give this one 10 dot. So what I'm going to do is, instead of doing this, let me make it as 65. Sorry, 35. If it is 35, definitely the mask will be different. If it is 35, this is not sufficient. You need to take up to here for host. We are giving from here for networking, so this is going to be 10.0.0.0/26, 10.0.0.64/26, 10.0.0.128/26. Goes like that. Because this 32 to 63 is already in use, we should not use this. We will start using from here, because from 65 we have not used. Only up to 63 we have used. So we can use this network 10 65 is the first IP, and then the broadcast will be 10.0.0.127. Last will be 10.0.0.126. So the first IP is 65, the last IP is 126. All right, somewhere around 62 IP address you're getting. It is okay. We need only 30. What I'm trying to show here is if you do subnetting using only this number, then a lot of IP address would have got wasted because you need only 10 and 20 here. So based on the necessity, you do subnetting. 10 is what necessity, so slash 28. 20 is what the necessary IP address, so slash 27. 35 is what the IP address you need, so it is 10.0.0.64 slash 26. You see, up to here is 24 plus 2 is 26. We call this as variable length subnet mask, VLSM. Variable length subnet mask, because the length of the mask is not the same. It's variable length subnet mask. Did you understand now?
Yes, sir.
Okay. I'm going to give you a homework. Kindly mute. There's an echo somewhere. Right? The homework is like this. You're going to have 3 routers, and you're going to have a point-to-point link. What is point-to-point link? You no need more than 2 IP address. One IP address here, one IP address here. Just 2 IP address. That is what point-to-point link. Point-to-point. We are not having a switch in the middle. You no need more than 2 IP address. Okay, R1, R2, R3. It's a point-to-point link. And then you got some computers here. Let's say you got 100 computers here. And here you got 150 computers. Here you got 90 computers. You need to do subnetting now. And the network that you should use is 172.16.0.0. The default mask is 16. Now you need to write the new subnet mask for each subnet. Will you do this, or you want me to do and show? Your wish. Whichever you ask, we will do it. If you want to take this as a homework, you can take it as a homework. Or if you want me to do it now, I can do it now. What's your option? What do you expect?
So can we another question as a homework? So and
Okay, I'll give you another
we'll
one
have
as
this
a
one in the
homework,
class.
then I'm going to do this. Okay, then the homework will be this.
Okay.
Take down. The homework will be again point to point, and 50 computers and 80 computers. The network is 10.0.0.0. Okay, that's all. So simple homework. Sorry. So mhm. This is your homework. Understand? Do you have any question?
Yes, sir.
Any question? No doubts?
No, sir.
Okay. Then will you be able to do the homework? Fine. I I hope you will find
I'll
easy.
try,
You
sir.
give a try, okay? If there is any difficult, let me know. It's a easy homework I have given. Not much, just 10 at work. There's one point to point, and another one is 50 computers. Another one is 80 computers. Even now itself, you can say uh, very easily what mask you will get. I can very easily say like that. But you may need some practice if you want to say like that. Give a try and bring it to class. If there is any correction need to be done, we'll do it in the next class. So subnetting is over. So we are going to focus on switching now. We started yesterday. We learned the behavior of a switch, functions of a switch. Switches listen to the incoming frame and learns the connected device MAC address from the source field of the frame. Once the MAC address is learned, there is no need for flooding. Only when there is a frame with unknown destination arrives, the frame will be flooded. Yep. So to avoid flooding, learning is important. Switches learn, hub don't learn. Hub always flood because there is no learning. Hub do not know who is connected where, so there will be always flooding. Switches listens and learns. Switches forward and also filter. Switches also flood. These are the things that we learned. Today, we are going to learn some interesting feature that is enabled by default on a switch. What is it? Loop prevention. Loop prevention is enabled by default. What I'm trying to say is loop won't happen in switching. Loop won't happen in switching because by default, the loop prevention mechanism called spanning tree protocol is enabled. Spanning tree protocol is enabled, so loop won't occur. Spanning tree protocol. You see, in some streets, in a new place, the shops are similar. And when you enter in one street, after 15 minutes of roaming, you'll be back in the same place. But for this 15 minutes, you are thinking that you are going somewhere. I remember once in Dubai, there is a place called Gold Souk. That's a big market, many streets. And I heard that not only gold is available, even the scent, Arabic scent, is very famous. Scent is also available in that some part of the market. So I started walking, hoping that I'll be getting into that particular street where the perfumes are sold. But almost after 20, 30 minutes, I came back to the same place where I started because the streets are very, very same, very similar. And every corner, the shops are similar. Everywhere, gold, 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 gold. Many streets of gold, many streets of platinum, many streets of silver. And I was going for 20, 30 minutes. I was walking, but after 30 minutes, I realized that it's the same gold shop, the Khan gold shop where I used to buy gold. I'm back to Khan. Good that I know that shop. Otherwise, I would have not found that, I'm looping. I was walking, 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 walking. After 20, 30 minutes, I'm back to the same gold shop, Khan Jewelries. Then I realized that I'm looping. The roads are confusing, especially when we walk without food. That happens. Loop can be avoided if there is some block. The problem in the street is all the streets are similar. And to divert you, you have some streets here, some streets here, some streets here, and not small, small streets. There are big, big streets. So let's say you started from here, keep on walking, 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 and you cross the road and you walk, 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 hoping that you're going to the place. But unfortunately, you came back to the same street, or you came inside this way and you came back, and you really do not know that you're going back to the same place. Because it's a long street, lengthy street, and you're back to the same place where you started. But you want to go somewhere here. You have an eagle view here in my drawing, so you know that I should have taken this road after coming out. But that eagle view was not available for me on those days. Internet was very costly. Roaming is very costly. I did not buy a local SIM card there, so no Google Map. Fine. How do we prevent it? Prevent this. If there is a block here, even if I enter like this, I would have come back and taken this road. Because there is no block, the loop happened. I entered here like this, hoping that there may be some perfume in this street. And then I kept moving, 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 thinking that I'm going towards the west, but actually I'm going towards the north again and coming back towards the east or south. So whenever there is a redundant path, loops are easy, possible. You see, you bought these two switches and you got some computers here, let's say some 10 computers connected here, another 10 computers connected here, and you have a wire connecting these two switches so that these 10 computers can talk to the other 10 computer. These 20 PCs can communicate each other via this single link. Now what will happen if that single link get cut? This 10 cannot talk to the other 10, isn't it? So what we can do is we can introduce another line. Why do we add this line? So that if this link goes down, the communication will still continue because there is another link. Your idea is good, but same like what I experienced in Dubai, packets will also experience. Packet that goes this way, let's say it's an unknown destination. Please try to answer me. If the switch receives a packet whose destination is unknown, what will it do? What will the switch do if it receives an unknown destination packet? Packet to an unknown flooding. So the packet, what is flooding? Sending via
Again,
all the ports other than from where it is entering. So it sends the packet in this link as well as in this link. The packet that went to this port on the top switch will again be flooded because this switch also do not know the destination. So flooding happens. Now you see the packet that went like this is also coming back like this. Same way, the packet that was going here hit here, and because again the switch do not know the destination, it floods again. So the packet that was going like this comes like this, and the packet that was going like this comes like this, and it's going to be a bidirectional loop. After few seconds only, total traffic jam because of the loop. Assume in a real world, if everyone who goes to office started looping here, 8 o'clock 100 people were there, 8 5 200 people, 300 people, 4, and full traffic jam. Because no one is exiting, everyone is in the same road only repeatedly. Same thing happens in the networking. Loop is very dangerous. It will consume the entire bandwidth. The packets won't go anywhere. It will be rounding, and packet will be keep on duplicating, and rounding again. How long? Until the whole bandwidth is consumed and switch gets crashed. To prevent this, this STP protocol, spanning tree protocol, is introduced. And I'm telling you, the spanning tree is enabled by default. That's why you don't see loop nowadays. Loop, because of redundant path, is not seen today because of the spanning tree. Loop, because of some other misconfiguration, is possible, but not because of redundant path. Now, how spanning tree prevents this loop? By blocking one of the port. If this port is blocked, assume. Now what happened? A packet is received, a known destination packet. The packet will be sent only on this path because the other path is blocked. And again, if this switch floods it, it goes this way and it comes this way down. Because there's a block, it will not come down. It won't come back to the same switch from where it originated. As a result, the block is prevented. Whenever there's a redundant path, by blocking one of the port in a link, the link will be made a standby link. And only one link will be active. Even if you have more redundant paths. Only one will be active, all the rest will go to standby because they all have got block. By doing this, loop is prevented. You see, I got 4 links, but how many active links? Only one. Can a loop occur? Not possible because the road is blocked in the other 3 paths. Only one road. How loop will occur? Only one road. How loop will occur? Not possible. Even if someone tries to come, there is a block here. It won't allow to loop. So you need to go back again. So blocking can prevent loop. By blocking, the switch makes those active link as standby. Why it is called a standby? In case if the wire get cut here, one of this will be unblocked and become active. Becomes active. So what I'm trying to say here is you got a redundancy. As soon as this link goes bad, immediately the standby link, one of the standby link becomes active, automatically becomes active without we interfering with it. You no need to get inside the switch to activate it. Who takes care of it? Spanning tree protocol. In first place, who was blocking it? It was that spanning tree protocol. You see, whenever we got redundant wires connected between 2 switches, spanning tree protocol will know that you got redundant wires and there is a loop going to happen. So before the loop occurs, spanning tree protocol will quickly go and block some ports so that only one link will be active. Spanning tree will do those things automatically. Spanning tree protocol will do this job automatically. It will keep only one link as active and rest all the link as a standby by blocking one of the port in each link. And if that one active link goes bad, it will remove the block from one of the standby link and make that standby to active. As a result, without losing any packets, the conversation between this 10 packet to that 10 packet, from this 10 PC to the down 10 PC will be keep on going. But again, I'm telling you, there will be some loss because the packet needs to switch over to another path. Earlier it was going in this path. Now because there is a link failure and this is made as active, all should go this way. The swapping time will be there. We'll talk about those things a bit later. I'm just giving you now the introduction to spanning tree. This is a very important topic in switching, so I do not want to rush. What is the job of spanning tree protocol? To prevent loop. How it prevents loop? Whenever it finds there is a possibility of loop, when we have redundant paths, there is possibility of loop. Spanning tree will know that there is a redundant path and there is possibility. It is possible to form a loop. So to prevent loop, what spanning tree protocol does is it blocks except one link. It blocks the port on all other link. And those links are standby links. They are not shut down. They are active, but they're live. They are live. They are alive. They are not dead. They are alive, but they don't allow any traffic to pass through. They are standby. Only if the active goes down, one of the standby will be promoted as active and it can forward the packet. In a blocking state, they will not forward packet. Blocking ports will not forward any packet. That's how we prevent loop. You know, for this you don't need to do anything. It is enabled by default. Let me quickly show you that. I got two switches and I'm going to connect more than one wire. You know, I'm going to have four wires and I'll show you there is only one wire going to be active. All the other three will be standby. See, I have not configured anything. I have not even logged into the switch. I just took two switches. I powered it on and I connected the wire. But if you notice here, there's only one green here. All the rest are red here. Uh, okay, the names are hiding it. If you see on this side, there is only one green. You don't need to see like this. We have commands to see. Let me go to the switch and show you using command. The command is show spanning tree. Look at this. There is only one forwarding. All the rest are blocking. BLK means blocking. They are used as alternate paths, alternate ports. They are in a blocking state. Only one is in a forwarding state. Why is this forwarding? Why not this forwarding? Why should these three block? Why not this one block and this one forward? We will discuss those things in our next class. There are a lot of things to know how the spanning tree will take decision. It's not randomly blocking one of the port. There is a procedure in finding a blocking port, and there is a procedure in finding a forwarding port. We'll talk about the procedure in our next class. So in today's class, we have completed VLSM, variable length subnet mask, which is the climax of subnetting, and we have started switching in our previous class, and we are continuing. We have continued today with this protocol called STP, which is a loop prevention protocol. I explained to you the logic how the loop is prevented. Loop is prevented by blocking the ports whenever we have redundant path. By keeping only one link as active, all the other links are made standby by blocking. For this, you don't need to do anything because spanning tree protocol is enabled by default. Switch knows that there is going to be a loop because there is a redundant path. There is a redundant wire connected. Switches can sense it using something called BPDU, Bridge Protocol Data Unit. That is what I'm going to say as a first word in my next class. How spanning tree protocol that knows that there is a redundant path by using a packet called BPDU, Bridge Protocol Data Unit. More about this is coming in our next class. So with the help of BPDU, they come to know that there's going to be a loop and we have to prevent the loop. So it quickly goes and finds the blocking spot, blocks it so that loop can be prevented. Do you have any question? All right. I
No, sir.